Okay, so I bring this up because I believe evaluations of today, you can evaluate it. I would recommend you wait until we do the course, but if, do evaluations before 5 p.m. on the day of common exam, which I believe is June 22nd. If everybody, responds, and everybody gets an extra 100 on their quiz scores. Obviously, I don't know who responds or doesn't, but go on the response rate. So take advantage of that. So let's get back to talking about these integrals. So the last time here was what we were kind of doing last time. We had some function here. And the motivating problem was to find the area under the curve. This is something that we really don't have the technology to do in the past because it's kind of over the top. But we're going to use these kind of calculus ideas. Now we have this thing called a Riemann sum. What we do is we partition the interval. That means break it up into the vertical pieces. And for every piece that we slice this up into, pick like a little test point. Call this x1 star. And that's my test point. And I plug that in to determine the height of the box. X2 star can be anything in here in terms of the height of the box. X3 star, etc. XK star is the test point K there. And we fill this up with box. Right? Now, this is an approximation of the area of the curve. All this is this is a height times a width, and then add them up. And that's all that is. The height is determined by plugging in a little green test point. That's what we did here. How did I know how far up to go? I used the function. Plug in the function that determines the height. And the width is delta xk. Step out. Anybody remember what we call this? Yes. That's right. So what this is how am I getting that number? I'm taking my test point, whatever I chose, and I plug it into the function. Because that black function there tells me where to stop. So that's what I do. I take that and I get the y coordinate from plugging in the function. That tells me the height. Get the y coordinate from plugging in the function tells me the height. That makes sense. Anybody remember what we call this kind of sum? And we have this thing called definite interval. And what do we do? Well, it's just one of these Riemann sums. It's just this Riemann sum, but we want to have it be more and more boxes, right? with some kind of limit, right? We're letting all the, we're filling this up with more and more boxes, right? These are too fat, let's make them skinny. Now, I did do this strange thing. What's this all about? This is I mean, I'm tempted to say, why don't you just let n go to infinity? Why don't you have more and more boxes? What's the problem with that? Well, if you let n go to infinity, which is a lot of what people do, the problem is that I'm unrestricted. Let me give you sort of an example. What if, here's my first box, and here's my test. Now, what if I let my number of boxes infinity by letting these get skinnier and skinnier? What if I let n go to infinity, but it fills this all up and it leaves this one fat? Right. So at the end of the day, the total area under my curve is going to be that box and then exact 0. It's still not going to be right, and it looks like my estimate is going to be too small because I'm missing this big curving chunk, right? How do I get around this problem? The problem was, so I let n go to infinity and I let that stay flat, right? And it's missing a bunch of stuff. This solves this problem because it says even the biggest box is getting as thin as you want, right? And this doesn't allow this to happen. This makes it be more uniform and spread out into more bits, right? So this is just a technical thing. Let me point out that in a lot of the examples that I have practically, when I ask you to compute these things from a limit point of view, what did I do when I set things up numerically is I made all my boxes be evenly spaced. Remember that? Just break it up into even chunks. If you assume that it's evenly spaced, now you can let n go to infinity, right? Because if you look at this one, it's not evenly spaced, right? Because this one's flat and so this thing is called the definite interval. And what the interval is, it is this limit. And we say the interval exists if this limit exists, and it is always the same. No matter how you partition it, no matter how you pick your decimal points. I have to tell you that because we want to, this is a math class, we got to make sure we're on solid footing. But as we go on, this may look all kind of strange now. How do we have all these different partitions? Let me give you kind of a word of comfort as we go on. It's actually so let me give you actually mark here. There is no reason now to always assume f of x positive. I've been talking about this in terms of variance because that was my motivation, right? Look at my function here is positive, I'm trying to get an area. But there's no reason you have to do this. Always we can find the interval from A to B, that's dx, the limit it's max delta xk goes to 0. Even if that's not necessarily. All that'll mean is for some of these values that is below the x-axis, we'll get negatives. Right? This delta xk will be positive. If you're in from A to B, then with this thing right here, you go negative. Here's a question for you. Let me try to write a picture of this. Everybody remember what means beyond? It means that the reflection is flip it over. Right? Remember, f of negative x is minus f of x. So if you want the y coordinate here, look at the y coordinate here and change the sign. So what this means is, this, that's supposed to be the mirror image. Everybody see what I'm doing? Anybody want to guess what this is? This is actually going from here. Total value of this is. This shape has some area. Got no idea what it is, but there's some positive area. Everybody agree with that? What about this piece right here? What can you say about this piece of image right here? If I had drawn it right, the area here, the actual absolute area here is the same as the area here. I agree with that. But this is under the axis. So when I'm computing the height, what's the height going to be? They're all going to be negative. So because my whole box is up here, this is making a positive area, and my whole box is hanging down here, make a negative area of the same size, same magnitude. So this should be 0. Those who get the cancellation. I'm going to highlight this later, but basically if you have an odd function on a symmetric interval, notice that the a minus a, the number here is the same. Then you always get 0. Those positive area, the same size negative area that cancel out. So let me stand up here. Let me draw a picture. So suppose we have this. This is the point semicircle. This has 1, 0. And this semicircle is going to 0, 1. And we'll say this is point 2, 1. And this is point minus 2. Minus 2. Okay, I want you all to think about this. And then I want you to kind of guess what the value of this is. You're actually close numerically. Something like that. Ah, very good. Everybody agree with that? It's observation. The triangles cancel. This one right here has an area. Let's see, this is 1 by 1, and then half base height. And this one's hanging below. So the triangles cancel out. So you got to worry about that piece right there. So you're gonna. Okay. So what's left over here? There you go. So it should be this. This bit is pi times the radius squared. What's the radius of the circle? 1. And then you're right. It's only half the circle. So this should be minus 1/2 triangle hanging triangle hanging down. 1/2 pi in the circle, and then 1/2 of the triangle sticking up. 1/2 pi. No limits, no nothing, right? That's all geometry. Okay, questions. Okay, so let me give you so what's that now? The area of the circle is pi times the radius of pi. Okay. Theorem, just kind of for your, I'm not going to prove this or anything. So, no. Let's suppose that F of x is continuous on David, or f of x is a condition bounded on David with only finite many this continent. So it's continued everywhere except maybe at a finite number of points. Then f of x is in. Now, this is something that I pointed out to you all before, that is easier in a certain sense. Theoretically, it's easier for a function to be integrable, to be differentiable, because there are continuous functions that are not differentiable. However, this says that any function that is continuous, you can integrate, right? And in fact, you only need, you don't even need continuity. In fact, this will even work if you have a function that's bounded and has only finite and then discontinuity. Let me ask you all this. How many of you have seen this function? Y'all see this 1040? This one is crazy talk right here. Let's look at this. One sine one. Keep it in some strange way. Well, when you start at one, where's the first place that it crosses? So, putting one, where does it cross the axis closest? Well, notice if x is 1 over pi, it's 1 over pi sine pi is 0. So this crosses the axis 1 over pi, which is about a third of the way in. Where does it cross the axis next? Well, the sine of 0, or the sine of pi is 0. The next closest sine of pi, the sine of 0 is 2 pi. Right? This will cross again, and this will cross again at half of that, 1 over 2 pi. The next place it crosses the axis, sine of 3 pi is 0. So 1 over. And 1 over 4 pi, 1 over 5 pi. Actually, in any interval between 0 and positive number, this crosses the x-axis infinitely. This is out of control, but you can't draw it. In fact, if you've got a graphic calculator or something, ask it to try to draw it and it will misbehave, right? Because it can't really do it. This actually, that's the great thing about the brain. I know this crosses the axis and 1 over pi, 1 over 2 pi, 1 over 3 pi, 1 over 4 pi. With notice that this function is not defined at 0. Right? Because you can't put it at 0. But I can do this. This function is not continuous. It's defined everywhere now, but it's not continuous because the limit, if x goes to 0 from the positive side, does not exist. It just puts them back. Doesn't ever settle. This function is wild and bad, but it is in it's bounded with only finite and many discontinuities. In fact, it's bounded between 1 and -1, and the only discontinuity is actually. So you can actually integrate this. I don't want to, but you can do. if you have this function right here. That function bounded, and when we finally do any discontinuity, integrate. You can differentiate this at every point. Right there, no derivative, only 40 places in there. And in the 1, 2, 3 places where it's not convenient, you can't differentiate, but you can integrate this. And I will tell you this is kind of fun. Y'all remember that if you're continuous, you don't have to be different, right? Because you've got point or a possibility, vertical tangents are a possibility. There are, now good luck writing this down, but there are functions that are continuous everywhere. And they are differentiable nowhere. Notice this function is differentiable in a lot of places, right? All the way up to here, down to this flat part. There are functions where the derivative doesn't exist at any single point. It's continuous everywhere. That's an extreme example of this theorem here, because there are functions where you can't take a derivative at any point, but are still continuous. Okay, so that's kind of just sort of theoretical folklore for you, in case you ever get a discussion about it. Any questions? Okay, so take this one.
But I think it's
We're going to get to it. Okay, yeah, that's right. It's the antiderivative is actually a different thing. The antiderivative is a tool that makes integration easier. And I'm going to give you an example where integration sucks, and that's going to make you appreciate when we get to the fundamental theorem of calculus. You might get to today. So, good question. So let's. So recall first. That the integral from a to b of x dx is limit minus delta x. K goes to 0, sum and x k star delta x. If this limit actually turns out to exist, which the previous theorem should tell you happens fairly often for your purposes, then so if I ever ask you to compute an integral using the limit, it's this. This is an important formula. If you want to get these actually using the limit. And also, why would you care about this? Because even if you can't compute this limit, this gives a good approximation. Anybody want to guess where this comes from? Yeah, that's right. This is the more specific form of this. This is evenly spaced. So where this comes from is, and I'm going to show you why it's true. Evenly spaced partition using right inputs to determine. And I put height in quotes there because my height could be negative. And but I'm gonna draw it positive here just to kind of help us out. Let's see where this comes from, and then I'll show you actually how to get your hands dirty and use a couple of examples. So here's my function. Now, this time, I'm going to evenly space my partition. Why? Because if the limit exists, then the limit exists for every partition. So if I want to compute it, let me pick an easy, right? Because if the limit exists, then it exists for all partitions. If it's integral, it exists for all partitions. So we'll just choose an easy one if we want to actually compute this thing. So where does this phrase back? Well, we'll assume n subintervals. This is A, so it's not x1, x2, x3, y. Let's call this xk minus 1, xk, n minus 1, and so this is going to be my representative here. Now, let's break this down. The width delta x of each interval is, well, how long is my interval? B minus A. Everybody agree with that? So the entire length of the interval, B minus A. And how many pieces do we split this up into? N, right? So my delta x is the same for all of them, but it doesn't vary. It's the same for all of them, and it's B minus A over N. Do I agree with that? Let's see if B minus A over N. It's coming up. Well, we'll just, I'm mindful that that's coming up. The endpoints. We're using the right endpoints to determine height. What are the endpoints? Well, they are in order x1, x2, x3, all the way up to x. Right, because I'm using the right endpoint. I never use a use x1 for the first, x2 for the second, x3 for the third, and so on. I agree. But I need to rewrite this. What is x1? In terms of stuff that I've got on my picture up here, other than x. So, is it A? Is x1 equal to A? No, it's a little bit to the right. If I agree with that. How far to the right? Right. Moved over one width. Three. What is x2? How many widths do I move over from A now? Right. X3. I move over 3. Anybody see the pattern here? What should XK be? You move over K, exactly. Perfect. Oh, that's a looking familiar. We'll be on a roll here. Now, this is the right endpoint of a interval. Right? Right. So height, and I put this again in parentheses because my height could be negative. My function goes below the x-axis. It doesn't in my picture, but good. How do I determine the height of the cave box? Well, I take my test point, which is the right endpoint, because that's what I've chosen here, and I shove it into the function, right? So that should be f of xk, which is f of a plus k b minus a. So area of case box. And again, I'll put my area in quotes because negative. F of xk, that's the height, comes delta x, because that's the width. So this is f of a plus k, b minus a over n, times delta x, which is b minus a over n. Yes. This is just xk. It's my test point. Right? That's just point. I got to plug that in the function to tell me how tall that box is. So this is just the point. Now I have to plug it into this function, and that y value tells me how tall the box is. So this is f of my test point that gives me a y coordinate that tells me how tall the box is. So the area, which can be positive or negative, of the cave box is the height, which is positive or negative times the width. And here I plug in xk is this thing, is that. So the signed area is add up all the boxes. B minus a over n is width. And notice B minus a over n doesn't depend on k, so I can pull it out. But now, this gives an approximation for n boxes. Right after I've kind of massaged the formula. Now take limit as n goes, and this gives you the formula. Questions? Now that we've gone to the trouble to derive this, let's use this. So let's actually do a couple times the same. I like this example because that's. Oh wait, anybody know what's needed with this? How do you mean? Okay, okay, so let's 1, 5. So let me put a couple points here. So I'll plug in 1 and you said 5. And then when I plug in 5, I'm gonna do 13. And so I describe this. And what's the general shape of it? Right, it's a line. Right? Notice this function is positive. So this should be just the area in the curve, right? So we don't need any fancy calculus, really, right? Let's get the answer and then test it, see if our formula works. How would I figure out the area of this thing? I guess it's trapezoid. Really, you don't really need to know. Fancy. How did you figure out the area of this area in the curve? That's perfect. That's exactly right. 25 rectangle. Okay, the rectangle here. This has height. What? Well, what is the height of this? 5. And the width is 4. So this area right here is 20. Well, the height here is the same as the height here. Okay, what about the triangle? What's the height of the triangle? What's it? Oh, there you go. 13, 5, 8. Everybody heard that? It should be an 8. And it's also 4. My scale's not very good. So what's the area of the triangle? There you go. It's a half base on the height, so it should be 16. So, good Lord willing, the creeks don't rise. This should come out to be 36. That's my guess. Okay. Here we go. Now let's do the fancy math and apply this formula. So I'm writing the formula down again, because to use this properly, we need to know what's going on here. We're the players in my formula, so K and N, but they're not affected by the specific problem. What's the function f of x? Agree. A and B. One and 5. So now, let's use this here. Let's see, B is 5, A is 1, so this is 4 over N times the sum of F of 1 plus K of 4 over B. A 1. Everybody okay with that? So right. Now what I gotta do is I've got to plug this in the function, right? My specific function is 2x plus 3. So that means double that and then add 3. So this is double this. So this is 2 plus 2k 4 over n. 2x plus. There we go. Everybody see where that comes? Plug this into that place x values. Okay. So let's continue. All right. Let me attempt to clean up that mess in there. This is the limit. N goes to infinity for 4 over n sum of 5. Here is 5, and then this is like k times 8 over n. Yes.
2, maybe, 4 and 4, actually 2.
2 times this and then 2 times that. It's 2 times the whole thing. Like 2. Oh, between 1 and 5, we've already captured that in this part of the formula. Because remember, this is 5 minus 1. That's where this 4 is coming in. And that's where this 4 comes in. Well, that's captured already in the essence of the formula. The formula is doing all that for us. All we're doing here is Replace X by this one. That's where the. I'll just clean it up a little bit. 2 and 3 is 5. There's 5. And I kind of regroup this a little bit. It's K times A over N. So I agree. Yeah, that's right. So I'm going to split this up. Over N plus 4 over N 8 over N. Uh, 20 over N. (32) squared all I did here is I pulled 5 out, leaving me at 1. Right? 20 over N. And I pulled the 8 over N out, giving me a 32 over N squared, leaving me. Now, just one more thing to do. Got to figure out what these things are. Forget the 20 over N. What is this? This is 1 plus 1 plus 1 plus 1 plus 1. You're adding 1 to itself n time. Where does that come to? There you go. You might remember what this one is. This is a little more complicated. It's 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. Very good. Very good. All right. So this becomes length n goes to infinity. 20 over n times n is 20. And this becomes 16. One of the n's cancels, n plus 1 over n. This is 20. And this is 16 of 1 plus 1 over n. I just rewrote this as n over n, 1 plus 1 over n. What happens to this thing goes to infinity? Well, 20 is not doing anything. Stay where it's at. 1 over n is 0.0. So I get 20 plus 16, which is 36. Which not only did it give me the right number, but it gave me the right pieces. That first bit, 20, comes from the rectangle, and the 16. Question. This is just adding 1 to itself n times. 1 plus 1 plus 1 plus 1. 1 added to itself 1 times 1. 1 added to itself twice is 2. 1 added to itself 3 times 3. This is n times. This is the formula that I gave you yesterday. And you don't have to memorize that, but you have to know to ask for it. You have to know that it's out there. Remember that when we added up the first k integers, the first k squares, formulas like that. Okay. Right here. You see where the 20 comes from? Right, because it's 20 over n times n. Cancels. The other one is 32 over n squared times n plus 1. 32 cancels down to 16. And 1 n cancels. So there it is in action. And to kind of build up, I'm gonna give you some more applications. So we're going to build a little bit toward fundamental theorem of calculus. Actually, let me do one more example. Just for fun. So six. Yeah. Just find value with. Now, this is not simply two areas because this is some crazy cubing. You have the technology now to graph it. But, so here. And then, okay, in this particular problem, where are my players? F of x is by the way, anybody want to take value? Could be 1,080. What's A? D is C. So what's the size? Yes. Darts, limit and goes to infinity. B minus A is 6 over n. Sum. This is going to be F 0. Take that. Plus K 6 over. But so this is the limit. Thing goes to infinity. 6 over n times. Okay, so I've got to put 6, 6 over n times k and x. Right, so it's going to be 4 times 6 over n k cubed minus 3 times 6 over n k squared. Right. Gosh, what a mess. Let's see. So this is the limit. Then goes 2, 6 over n. Sum. Okay. 6 cubed is 216. 4 is 860. Over n cubed times k minus 6 squared is 36 times 3 is 108. N squared is all I did is express my numbers probably. All I did is cube this through 216 n cubed and 4 864 n cubed times k cubed. That's 3 times 6 squared plus 108 n squared. What's in it? So I'm going to do the same thing that I did before. Just kind of break this up into pieces. Ooh, I got 864 of n cubed k cubed. Minus 6 over n. 108 n squared k squared. I said separately. Okay, well, this is a bit of a mess, but then Jim goes to infinity. I'm all right, he's doing separately, which I can do a big open stuff. This is, I'm gonna pull this 864 out, so that's like what 5184 over n cubed. Minus, pull that 108 out, and 648 over n cubed. Oh, I'm sorry. That should be in the 3 and 1 is 4. 2 and 1 is 3. So. I gave you guys both of these yesterday. Gold star, if you remember. You might remember what happens minor first squares. That's right. Remember the one that you like because it's got a 6 in it. Yeah. Right. N plus 1, 2n plus 1 over 6. And this one was like n squared, n plus 1 squared over 4. So let me write this out explicitly. When n goes to infinity. Let's see, this is 5.84 over n4 n squared plus 1 squared over 4 minus 648 over n cubed n plus 1 2n plus 1 over 6. Actually, this is when n goes to infinity. 4 and 5.184, that's 1296. Over n squared, n plus 1 squared. Four cancels down to 1296, and 2 powers in here. This cancels down to like 108. 1 power cancels like n plus 1 over 2n plus 1 over n squared. Now, this bit right here is n squared plus 2n plus 1 over n squared. And this bit right here is 2n squared plus 3n plus 1 over n squared. And all I did is go multiply on the top here. And multiply. So this limit thing goes to infinity of 1296 times 1296 times 1 plus 2 over n over 4 squared minus 108 times 2 plus 3 over n plus 1 over n. Now, as n goes to infinity, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So what am I left with? 1296 times 1 minus 108 times 2. That's 216. Wait, 1,000. Any questions? That is the intriguing part, is right? Do you think I did all this in my head? No. Well, it's okay. But I did. I certainly did not. Right. How did I? Right. Wouldn't you like to have a piece of that action? Right? Wouldn't you? And if you've noticed, everything I've done so far, polynomials. Let me give you kind of kind of a disturbing. So I'm not going to finish this example because it stinks. You can do this though, if you persevere. If you look at this function here, A is 0, B is 4, my function square root of x. Well, so again, limit z goes to infinity. B minus a is 4 over n. That's the sum of this is going to be 0 plus k 4, so the square root of 4 over n k. Now, out, and we're starting to see some limitations now. K equals 1 square root 4 over n. K equals 2 square root 8 over n. 3 square root 12 over n. Square root of 8 n minus 1. And every one of these other problems, I had the sum under here that I had a formula. Right? I got down to adding squares and I was like, oh, look, I've got this. Right? Oh, look, I've got a formula for my book. Oh, look, I don't have a formula. This, so how are you going to get this? Because remember, I turned these sums into a nice little formula that had only n in it. How do I turn this into a nice little formula that only got n in it? That's hard. And square root is a pretty routine function that you want to be able to do. So nobody wants to do this limit. And I'll give you another piece of bad news. Replace the square root function by, say, sine x. And so now we get, so I'll do this in red. If we replace the square root function by sine x, then instead of this, we have sine of 4 over nk. And this would be sine of 4 over n, sine of 8 over n, sine of 12 over n. And that's pretty simple, right? Nobody wants to be doing that. Right? And square root of x, sine x, these are pretty pedestrian functions, things that you will probably think would show up in engineering problem, science problem. How are we going to deal with that? Right? So we've got a couple of things. Number one, how did I do that in my head? Number two, how do I can't even deal with this, right? I mean, I could, but it's going to spend, I'll take all afternoon doing some crazy limit, figuring this out, maybe do some conjugate, who knows what I'm going to do. It's going to be awful. We need to get around this, right? And that's the motivation for what's coming up. Before we do this, I'm going to give you some properties of integrals. I think that we may have used a couple of these, and some of you may have kind of guessed this. Let me give you kind of another little sort of pointer. When you go to 1080 next semester, you're going to have integrals coming out your ear, right? All kinds of applications and things all over this, right? The application sections in 1080 force you to hydrostatic pressure, finding centroids, finding all kinds of things, finding work, all those kinds of things. If you remember Now, and we're fixing, we're right on the cusp of learning a fancy way to do these kind of problems. But don't forget the old school. Don't forget your roots, right? If you remember that an integral is a limit of sums, and remember that, then the application problem is much easier. So this integral, it comes from this. If you remember that an integral is actually a limit of sums of this form, right, where you take little widths and little heights that may be positive or negative, it will make a lot of your stuff in the future, right? You're going to get fancy ways to work this side of the equation out, but if you remember this, when you do computational applied stuff, or when you need to approximate, this will make your life easier. So mark my word, remember this. Which do you think is easier, adding things up or integrating things? You would certainly think that. However, I'm going to teach you a trick that's so good that integration for many functions is easier than that. So so this is just kind of fun. Here's what I'm gonna do. I'm gonna add up a lot of terms to this. Right? The first term is 1/3 log 3 log log. You can find that term's about 4. It's about, then the next term is 1/4 log 4 log log 4. And that one's like maybe 1.5 or something like that. Now I'm gonna add up this many terms. Now, how many terms is that? Anybody give me an idea for how big it is? 10 to the 100th power. Anybody know what that's called? It's actually called a Google. That's where Google actually got its name. They stole that term. Only Google is spelled different. It's 10 to the 100th power. It's 1 followed by 100 zeros. In old school calculators, that would be the number where you get an error because it'd be too big. Now most good calculators you hire it. That is called a Google Plex. That is 1 followed by Google zeros. Let me put it to you this way. This number is so big that you can't even write it down in standard notation. Suppose I wanted to write 1 and then a Google of zeros after it. There's only about 10 to the 85th subatomic particles in the universe. So there's not enough material in the universe to write that many zeros after that. That's how big that number is. Right? So in fact, you would, to get a Google, to be able to write this number, you would need the number of subatomic particles in about 1 trillion universes size ours, just to write that number down in standard. That's how many of these terms we're adding up, right? 1/3 log 3 log 3, 1/4 log 4 log 4, etc. What does this add up to? Ballpark. That's a lot of terms, right? You're adding a number of terms that's so big that you can't even write the number down in standard. It's physically impossible. And the first term of this is 3. So if I add up that many term, next is about 1.5. How much is that add up to? A lot? You would think, right? You're adding a whole lot of things. This is about 10.1. Good luck in the computer. Right? A computer can't do this. You can't have it. However, you can approximate this to an interval. And you can do this. You can get, in fact, one of the things I did in 4190 class a couple of semesters ago is estimate the sum within a 10. And it's about this, I think, within about it, right? It's impossible to add it up. It's just too big. But you can use intervals to approximate. So that's another application. Okay, let me give you some properties of integrals. And some of this I'll kind of briefly explain. Let's suppose f of x and g of x are integral. That is, this limit exists on an interval containing A, B, C. So these are just three numbers, and I'm just saying that the interval contains these. Number one, I bet you can guess this. What do you suppose the integral from A to A is? Well, think about it. So draw a function here. A to B approximately gives you an area, but it's positive. What happens if you start at A and end at A? What's your area going to be? There you go. Number two. This is kind of silly, but it's later. If you reverse the order of integration, then you change the sign. Basically, reversing the order of integration is you're integrating backwards. So now you're changing x is going to be negative. So it's just going to change the sign and everything. Right. So you're going from B to A and you're measuring x backwards. Right? That's kind of intuitive, but we'll go for that. If k is a constant, let me ask you this. So again, here's my preaching limit of sums. Can you pull constants out of sums? Sure you can, right? If you've got a constant thing, you can factor it out. Can you pull constants out of limits? You bet. You pull constants out of intervals. Because an integral is a limit of sums. This is a limit of sums. You can write the sums separately. If both limits exist, you can do the limits separately. So this works. Let me point out that if you put 3 and 4 together, you can also mean to replace the plus and minus there as well. So you can split up sums and differences in intervals. This one is kind of fun. Number 5. The interval may be that x is the interval base c after base x plus the interval c. Now, if I draw you a picture of this isn't proof, but intuitively, I'm a picture of it. Here's what this says. Here's what this theorem says. Now, again, this is not a general proof. This is showing you what's on in the special case here. This is the total area under this curve all the way from A to B, right? This first piece is the area from A to C. Second piece is the area from C to B. All this is saying is the total area under this curve from here to here is this area plus this area. All the same. One of the things that's interesting about this theorem, though, is nobody said, I didn't say in the theorem that C had to be between A and B. This is also true if it's like this. So the area from here to here is the area from here to here plus the area from here to here. But remember, the area from here to here is going backwards, so it's surprise on. So you don't even need to see the end. What's that? It won't be. We're going to see it. I'm actually going to, when we talk about fundamental theorem of calculus, we'll need this. But you're right, it is common sense. And this one right here seems silly too, doesn't it? Right? You're integrating nowhere. But actually, it's funny how lots of times that'll get you in math. Things that you think, oh, okay, that's obvious, they actually come in sometimes and pay off. Here are some boundaries. If f of x is greater than or equal to 0 on AB, then the interval may be f of x. This one, I bet, guys probably have your head wrapped around pretty well. What this says is, if your function is above the x-axis, then this interval is an area. And that's all it's saying. An area is like the prevalent. I can make a more general statement of this. If you have big function, little function on this interval, then the interval may be that that's the x greater than the interval may be given. So you have a bigger function and you have a bigger interval. And again, all you have to do is kind of sketch a drawing to see why this is true. At least in special case. And finally, if I'm going to use this too, so if your function is between these two numbers on this interval, which is continuous, bounded by this, then the interval may be f of x dx greater than or equal to m b minus a capital. So these are two concrete numbers that help. Let me draw you a quick sketch of why that's true. Not proof again, but simply to get an idea. What we're saying is on the interval from A to B, your function f of x your function is greater than or equal to m your function is the black function is above this. And it should be less than this maximum capital N. Let's reach it. Would everybody agree that that picture gives me what I want? Right? Every y coordinate on that function is less than or equal to m, but greater than or equal to little m. Right? So the area under the curve everybody agree that the area is bigger than or equal to this rectangle down here? And the area of this rectangle is height. Yep. And it's smaller than the rectangle that has the green top. Height. Okay. Any questions? What's up? You need to know it, right? I mean, just in a lot of these, integrate nowhere, you get zero, flipping reverses the sign, you know that. When you pull out constants, break up some. And this one, we're going to see some more of this action there. Let me actually give you. Actually, this is kind of a warm up. What do you call it? This is my t-axis. Y equals 2t. Now, I'm not really doing this. You guys, I want to practice one more of these intervals here. But I bet you all can do this. I'm just going to do this one more easy right here. I'm going to call that x. I want a of x equal to area underline of so really what I'm doing here is I'm using this line. My line's not my function, I'm just using it to do this. This is a of x. So my function measures the area under the line as I go from 0 to x. That's all I want. In fact, one way that I could write this function, actually, now that we have our notation, is a of x is, you guys help me out. What is the area under this? Let's see. What's the width of my base? X. Okay, good. And I just want to need height. So the key coordinate is x. What's the y coordinate give me the height? 2x. I agree. So ax should be half base. Height. Everybody agree with that? So a of x is actually x squared. Notice when x equals 0, got no area. When x equals, say, 2, right? Then I've got a triangle of width 2, height 4, which gives me 2 squared. 4. So everybody agree with such? What's the derivative? Notice the derivative is similar to the line that I used to find the function. Let's try this with something else. So this will be the last exam. We're going to take a quiz, and this will give you something to sort of cogitate. Oh, I did want to. So. Find this 3 squared from this one's a little harder. I can't do this. I need to sort of drive my point here. I'll do so. So this is x, and this is x, 3x. Everybody agree with that? And the area that I'm trying to get is ax. Everybody agree with that? Now, ax, this is why I call it interval function. What is this really? Which is, in our case, my function is 3 squared. I agree with that. Because really, me finding this area is me. What if we learned that the interval actually gives you the area, since this function is above the x-axis, it gives you the area of that, right? So really, a of x is really this. So let's try to figure out what a of x is. So now, which is lim as n goes to infinity of b minus a m f of a plus k b minus a n a 1 n. And here my players are a equals 0, b equals x, and f of x, or f of t, in this case, is 3 squared. So this is lim as n goes to infinity of x over n. This is going to be 3 times, see, a is 0, this is x over n times k. So what happens when I put this thing into so this is the limit, z goes to infinity, x over n. Three x squared over n squared k squared. Now I'm going to pull a bunch of that garbage out. This is lim, z goes to infinity. That's going to be 3x cubed over n. Sum X. So I pulled out 3x squared. 4x, 3x cubed, n squared at the bottom. And now, I seem to recall this thing right here. N 1, 2, and 1 over 6. Then, infinity, 3x cubed over n cubed times n plus 1, 2n plus 1 over 6. Yes, that's 6 here. So this is infinity. 6 cancels out half x cubed. And this becomes n plus 1, 2n plus 1 over n squared. So the 3 and 6 cancel out 2 there. Got my x cubed still hanging around. 1 power then cancels that. And I have n plus 1, 2 plus 1 over n squared. Now this bit, this complicated quite well. This bit is 2n squared plus 3n plus 1. So this is then 1/2 x cubed times divide this by n squared 2 plus 3 over n plus 1 over n squared. And as n goes to infinity, these two might get 1/2 x cubed that's kind of cool. My area formula is just the cube of how far I go out. So if I go out 1, that means that area is 1. Right. If I go out 2, the area is 8. If I go out 3, the area is 27. Notice the area is growing very fast compared to how far out to the right. Any questions? So this is exactly the same problem we've been doing before, but check this out. What is 8 pounds of x? Where are you? Square. Notice there's a similarity. It's not a coincidence. In fact, this is a mirror. And we will discuss this right on the cusp of this. Next time we're going to talk about fundamental theorem of calculus during these problems. Any questions? I do have one more thing I'm trying to get up. Might come out useful. Thank you. We're actually going to get to this later. I'm going to actually show you what's true later. Let me. Then we have an interval minus a and a that equals x. Now you need it to be odd and you need to be on the symmetric interval. All right. Are you okay with that? Because remember how the areas are forming cancel out. positive. Great. Now, odd functions are functions like sine x, x cubed x, tangent x is odd. Anybody want to guess what happens to even functions? If you have an even function. Oh, very good. So now, when you have an even function, this is what it is. And in this case, integral from minus a to a of f of x dx is twice integral from 0 to a. It's not quite as much. But so what it's saying is the area here and the area here are the same. So anyway, we're going to actually justify this later, but for now you can just take that as a given. Any questions? Okay, let us do the quiz.